Hi guys and welcome to GP Academia. In this video, I will discuss statics. I divided this topic into two. First, the equilibrium under the action of concurrent forces. Second, the equilibrium of a rigid body under coplanar forces, wherein we will extend our discussion to those bodies that can rotate. Let's start. Let us start by defining concurrent forces. Concurrent forces refers to those forces whose lines of action passes through a certain common point. And for this example, it can be a point on an object as illustrated here. We have a certain mass m hang using two cables attached to the wall. So this is the wall, ceiling and the wall, wherein we have two cables attached to a certain mass m. We can draw its free body diagram as shown at the right. And shown here, we have three forces. All our forces for this case passes through a common point, which is this one, the origin of our coordinate axis. An object is said to be in equilibrium if under the action of a given force or concurrent forces, the object is not accelerating. And we have here the first condition for equilibrium, wherein the summation of the forces is equal to 0. Or in terms of its components, we have this expression. The resultant of all external forces acting on a given body must be equal to 0. Generally, we can solve problems for equilibrium under the action of concurrent forces using the following steps. First, isolate the object given in the problem. Second, draw the free body diagram. Show all the forces present in the problem. Third, find the components of each forces with the help of your free body diagram. Commonly, we have two-dimensional problems, so we have x and y components. Fourth, use the equilibrium condition shown earlier. And last, of course, solve for the unknown. Can be weight of an object or a certain force. Let us write this problem for the first condition of equilibrium. We have this scenario wherein we have three tensions present in our system. So we have this mass, we have this cables on wall and the ceiling, and we have this free body diagram. We have three forces, so T1, the tension 1 is given, which is 25 newtons. Then we have T2, which is unknown. Then T3, this one, is just equal to the weight of the object hanging from it. Using the first equilibrium condition, we can write the following expressions. So we have first the summation of the forces along the horizontal, which is equal to 0. And we just need to get the x components of our tension. So T1 minus T2 cosine 40. So this is 40 degrees. This is 40 degrees. And therefore, we have this expression. And this is equal to 0. And this is our first equation. Next, we get the equilibrium condition for the y components. So we have here T2 sine 40 for the y component of T2. Then we have minus W, which is the weight of our object. And therefore, we have this second expression. We can easily solve this problem given that we already know the value of T1. And therefore, using our first expression, which is this one, we can solve for T2. So our T2 is equal to 32.64 newtons after we substitute 25 newtons for T1. Then we already know T2, and therefore we can use this second equation to solve for W. For the weight, the value of the weight is 20.98 newtons. Next, we have a scenario wherein forces are not concurrent, but they lie in one plane. These are coplanar forces. An example of this is this illustration. Let's say we have these two people holding a log with a weight W. So this weight W is placed at the middle of our log. Thus, we are exerting upward forces F1 and F2 to balance the weight W. Before we officially discuss the second condition of equilibrium, let us review what is torque. Torque is useful in solving equilibrium problems for coplanar forces. Torque on a given axis due to a force is just a measure of the effectiveness of the force in producing rotation about a certain axis. It is defined by this equation. So tau is equal to Rf sine theta. So this refers to the magnitude of your torque, or this is equal to F times the lever arm, which is your R sine theta. The R here is the radial distance from the axis to the point of force application, and theta, this one, is the angle between the line of action of R and F. Given that the lever arm is just R sine theta, we can express this one, R sine theta, as the lever arm. Now, we have two conditions for equilibrium. The first condition, or the force condition, as stated here, is this one. It states that the vector sum of all forces acting on a body must be equal to 0. And this is similar to what we have discussed earlier. The second condition, or the torque condition, so we take an axis perpendicular to the plane of our coplanar forces. The summation of the torques must be equal to 0. And taking note that the counterclockwise gives a positive torque by convention consistent with the right-hand rule. Okay, so now let's have this sample problem. Klee and Leona carry a uniform 6 meters log with weight of 200 newtons. Klee is 1 meter from one end and Leona is 2 meters from the opposite end as shown here. What weight does each person support? And this is the same illustration we had earlier. We have this weight placed at the middle and we have this force F1 and F2. So what we can do here is, of course, first try to analyze the problem and define our pivot point, wherein the object rotates about this axis, located, for this case, at the location of this first person with the force F1. And therefore, let's have this drawing below. We have these three forces. The force 1 is located 1 meter from one end, and this force F2 is located 2 meters from the other end. Therefore, using A as our pivot, we can have this summation of torques, or the second condition of equilibrium. First, for F2, so remember that F1 has 0 lever arm, and therefore we will not consider that one to our summation of torques, because R here is equal to 0, given that this is our pivot point. So for F2, we have 3 meters from this point A. So this is about 3 meters times F2, the magnitude of this force, sine 90, minus 2 meters W. So this is the distance of your W with respect to this pivot point A. Sine 90 is equal to 0. Therefore, we can easily solve for F2, given that we know the weight of our log, which is 200 newtons, and therefore the value of F2 is equal to 133.33 newtons. So next, let's try to get the summation of the forces along the vertical, and this is equal to 0, following the first condition of equilibrium. So for this system, we have F1, which is going upward, so that's positive, F2, positive as well, minus W, and this is equal to 0. And therefore, we know the value of W, we know the value of F2, which is this one. Therefore, the value of F1 is equal to 66.67 newtons. Now, given this system, let us find the torque about this axis A, located here. And we have these three forces F1, F2, and F3. The length of this is 70 centimeters. So note that tau, or the torque, is equal to Rf sine theta. And first, let's try to get the torque for F1. So the force F1 produces a negative torque given that it rotates the system clockwise with respect to this axis of rotation E. And therefore, we have this expression, negative L, the length of this, F1 sine 90 degrees. So this is 90 degrees. And therefore, we have the value of negative 10.5 newtons meter. Then for the second force, F2, the value of our torque is equal to 0, given that the line of force, this one, passes through the axis, which is this one, the A, our pivot point. And therefore, the theta here is 0. So sine 0 is equal to 0. And therefore, tau is equal to 0. So last, for our third force, F3, it produces a positive torque given that it rotates the system counterclockwise. And by convention, that produces a positive torque. And therefore, we have L, the length of this, F3 sine 25 degrees. So this is 25 degrees. And we need to get this one, the lever arm with respect to our pivot point A. And therefore, tau here is equal to 10.35 Newton meter. So let's try this last problem. We have a 10 kilogram beam, this one, and 3 meters long, that is used to support a 20 kilogram sign using a cable attached to a building. So this one, the green. Find the tension in the cable and the compressive force Fx exerted by the beam. So this is the illustration, and we have the following values. And we need to find the tension T, this one, and this compressive force Fx. Let's start by finding the value of this R that is perpendicular with respect to our cable in order to get later the torque due to this tension T. So we can get this value, or get this R perpendicular, which is equal to L sine theta. We know our L, which is 3 meters, and this is just 40 degrees, and therefore the value of this is 1.93 meters. So next, using the second equilibrium condition, the summation of the torques is equal to 0, and therefore we place our pivot in this point, and therefore we can first get the torque due to this tension T. So we have T, then we have this R perpendicular, so which is just your L sine theta, or the lever arm, minus the weight due to this beam, which is located at the middle of the beam, which has a length of L, so that's L over 2. That is sine 90, of course, perpendicular with respect to our pivot point. Then it produces, of course, a clockwise rotation, and therefore we have a negative torque, unlike your tension, which produces a counterclockwise rotation. So last, we have this mass M, or our sign, and we have this weight MSG times the length L. It is located at the end of our beam, and this is equal to 0. And therefore, we have the following values. We can get the value of our tension, which is equal to 381.22 newtons. So next, using the first equilibrium condition, we have this expression wherein the summation of the forces along the horizontal is equal to 0. And therefore, this is just equal to Fx minus T cosine theta, using, or by getting the x component of our tension. And this is just equal to 0, and therefore we know the value of T. So Fx is equal to 292.03 newtons. And that's it for this lecture. Hi, if you have learned something in this video and you like my content, please consider subscribing my YouTube channel, JP Academia. See you in the next video.